into a slightly different approach we took compared to previous work. If we look at some part of the cellular stack as shown on this slide, we inject or focus our fuzzing efforts on a subpart of layer 2 in the stack. To do this, we needed to overcome a couple of challenges. For instance, like creating all the fuzzing tasks and the possibility to do fuzzing. We need to overcome roadblocks and also do over-the-air replication of findings. But having all of this done, we are getting to something like this. We have crashes found in emulated fuzzing, we play them over the air, and we can see them triggering on real phones, mostly indicated by connection bars disappearing and people not being able to do calls or anything anymore. And an especially interesting part of all of this is that while we focused our fuzzing on layer 2, most of the functionality we explored and where we find vulnerabilities in were in layer 3 of the cellular stack. So let's get started and talk a little bit about cellular basebands.
So modern phones typically consist of multiple processors. There are two main processors, which is your application processor and your cellular processor. The application processor is typically where Android is run on, and then the cellular processor is responsible for all radio connectivity. The cellular processor is also referred to as the baseband, which is also the term that we are going to use throughout this talk. The baseband itself implements all of this radio connectivity by like millions and millions of lines of highly proprietary code. There are a lot of very interesting parsers. There are a lot of obscure features, and therefore it implements most layers of the communication stack. And all these goodies are then reachable via either sending radio packets over the air or sending internet packets. So all in all, it's a very interesting service to look at.
And Dyon mentioned that there is a lot of attack surface. So let's look into how the firmware running on these cellular processors, the basebands, usually look like. Most of the time they are providing some sort of customized and proprietary real-time operating system, which basically implements everything which you wanted from an RTOS, right? Like you have a scheduler, you have timers, you have interrupts, you have messaging, and you have tasks, which in the context of a real-time operating system is basically a process. Like what we know on a desktop computer as a process is a task in a real-time operating system. And despite this, so despite the RTOS itself, the firmware running on basebands implements the cellular stack. The cellular stack is specified over a lot of different specification documents and distinguished in a lot of different layers. And what we see in most implementations is that these different layers, as specified in the specification, are one-to-one mapped into so-called tasks. So during this talk, we will use the terms task and layer sometimes a little bit interchangeably. The task, so the layers of the cellular stack implementation, do communicate with each other using the message queues provided by the operating system.
So in recent years, we see a very awesome shift in baseband research. So on the slides, which is either on the right or the left, these are just a few examples of baseband research in 2024 and 2023. So there are also two examples of talks here in hardwear.io, which is the Basebanheimer and the How to Hack the Shannon baseband talk. And in that extent, we are very happy to extend the work on baseband research here at hardwear.io.
But if we look at most of the previous work of research on cellular basebands, at least when we started our research, we saw that most work focused on the cellular layer 3 and the functionality being in this layer. This has been a little bit different recently, like two of the more recent works also look at vulnerabilities in layer 2. But back when we started our research, we thought, hey, let's look at layer 2 on our own. And we also thought, let's start with the legacy stacks first. This has two pretty great upsides. First of all, these legacy stacks, so basically 2G, even though we want to expire 2G, it's still there in all of the phones around. And it's a legacy stack written over 20 years ago with a lot of custom written parsers, and it's all still reachable in most of the phones around. Additionally, 2G does not provide mutual authentication, so while the network tries to establish that the phone is a valid subscriber of the network, the phone would not establish trust of the network. Which means, as an attacker, we could very easily mount a fake base station and attack the phone over the air. And we looked first into GSM layer 2, which is not the focus of this talk, but instead we also looked in GPRS, which is what we want to be talking about now. So what is GPRS?
So some of you may be familiar with GSM, but what is GPRS? So GSM is a circuit switched service or protocol, and this means that it doesn't really work with packet switch oriented services such as the Internet Protocol. So the solution for this was to introduce something called GPRS, or General Packet Radio Service, or 2.5G. And the idea is that if you want to use a circuit switch service, such as calling someone, it will use the GSM protocol. But let's say you want to connect to the internet on your phone, it will use the GPRS protocol.
And let's have a look a little bit into the protocol stack of GPRS more in depth. So it's split in 3 layers, and unsurprisingly, as with most network stacks, layer 1 is a physical layer. As we're talking basebands, most of the times they do want to communicate over the air with some cell towers, so we have some antenna attached, and getting radio messages in over the air. On layer 2, we then have 3 subcomponents, medium access control, radio link control, and logical link control. And the MAC layer is responsible for scheduling and similar of the things coming from the physical layer and reassemble it into small segments for the radio link control layer, which then in turn formats them into frames for the logical link control. And the logical link control then looks at these reassembled frames and decides to which layer 3 task the incoming packet should be forwarded to. And as first on layer 3, we have, again, 3 different sublayers. We have SMS, which I think is widely known, right? Short message service. Interestingly, we also have this in GSM. With a different in GPRS, we can have longer short messages. Then there's SNDCP, the Sub-Network Dependent Convergence Protocol. While this may sound like a little bit complicated, you can think about of what makes the baseband connected to the internet. So here we are basically dealing with IP and the internet protocol being able to talk via packets with other computers out there. GMM is the GPRS mobility management. So here we are dealing with things like to which cell tower are we currently connected and similar. What we saw in implementations is that from the GMM layer, we can also reach 2 additional layers of the GPRS protocol stack, which is A, SM, session management, and B, SS, supplementary services. Supplementary services, for instance, help to supplement all the other parts of the stack. One example would be to have a bearing of SMS messages, so to block receiving of SMS messages. The other thing, session management, is there as we now have IP and packet-based communications, we will need to keep track of some context, so we need to manage some sessions, and that is what SM is doing. With this high-level overview of the GPRS protocol stack, let's dive into the layer 2, and in particular in the logical link control.
So an LLC frame will typically consist of multiple fields. The most important field is the protocol data unit field, or the PDU field. And then the PDU field again consists of several other fields. Not all of them are as important, but we do want to stress the information field, because the information field is actually the field that contains the layer 3 data. Then there is the address field, which contains the service access point identifier, or the SAPI. And this is actually really important to understand the forwarding logic. And this is also what we're going to explain. So the forwarding logic itself is based on the SAPI. And let's say we start at the LLC layer. So we get a message into the LLC layer, and the LLC layer may want to forward this message to another task. Let's say we use the SAPI 3, for example, then we can follow the arrow to the SNDCP task. Let's say we use the SAPI 7, for example, then the message need to be forwarded to the SMS task. If we use the SAPI 1, it will be forwarded to the GMM task. Now, the GMM task may also be able to forward the message, but we already use the SAPI, so we can't use it anymore. And for this, we actually use the information field, or the first byte of our information field. We can see if that value is 10, it will forward the GMM task, will forward the frame to the SM task. If the value is 11, it will forward it to the SS task. So in general, depicted in red is the layer 2 functionality, and depicted in blue is the layer 3 functionality.
So that's it for now with a high-level introduction into GPRS, layer 2 and 3. Let's look into our approach to fuzzing, or how we try to tackle this complexity of a stack for fuzz testing. So we decided to implement our fuzzing using the firmware emulation framework, which came out of previous research. Generally speaking, if you want to fuzz test a phone, you have multiple options. One, for instance, is testing over the air, just sending a lot of messages, seeing what happens. The problem is basebands are proprietary and heavily closed down, so we cannot really see what is happening there. That is why we went for the full system emulation approach, so we can put the baseband firmware inside an emulator and just have it running. The firmware framework supports MediaTek and Exynos baseband firmware, and it has some advantages, like it spills out all the logs the baseband will produce, it has coverage tracking inclusive, and it has very nice integration with AFL++, so we can directly use one of the state-of-the-art fuzzing frameworks to attempt fuzzing the baseband.
So a fuzzing task in firmware is actually injected into the real-time operating system, and this means that our fuzzing task will actually appear as an ordinary task for the cellular processor. And the main advantage of this is that we can use the baseband's primitives. So for example, we can use the baseband's primitive to allocate memory, or for example, to send a message to another queue. There is also an AFL wrapper, which we use to get our fast input and communicate with AFL++. And then the fuzzing itself actually consists of a setup phase and a actual fuzzing phase. And the setup phase is the pseudocode on the slides now. We can see that we need to set some magic values. We need to allocate some memory, again with the baseband's primitive of the palm alloc, which is just an allocation of the baseband. And then we can see that we set some magic values and then finally send the message to the task that we're interested in. We can see this PAL message send to function, and this is just the baseband's primitive of sending a message to another task, in this case the task that we're interested in. Then there is also the fuzzing itself. It is really similar, but in this case we actually need the fuzz input, which we get from the getWork function, which is just the fuzz input from AFL++. We again allocate some memory, set some magic values, but this time we copy over the fuzz input, and then we send it to the task that we want to fuzz.
So with this in mind, let's look at the fuzzing strategy we had. And the existing emulated-based fuzzers basically opted in for one of the following approaches. Either it would pick one specific parser or one specific function, in this example some ASN.1 decoder, and try to specifically fuzz this functionality in itself. Another approach with a firmware framework would be to create a fuzzing harness for one specific task, so one specific sub-functionality of the cellular stack, in this example the session management alone. But what we wanted to do with our approach of GPRS fuzzing, we thought, hey, if we are able to build a very good fuzzing harness for the LLC layer, we can have the LLC layer forwarding the incoming fuzzing input to whatever other task of the stack which is above it. Right? The idea, with enough of initialization, we should get there and can write a single harness to explore all the other functionality.
To do all this, we use a firmware image from a Samsung Galaxy S10e. The phone itself is from 2019, but the actual firmware image itself is from 2023. The main intuition behind this is that it is simply the latest phone supported by firmware, and furthermore, the original bugs or the bugs found in the original firmware work has already been patched out in this firmware version. So we would reduce false positives. However, to make this happen, we needed to overcome a set of challenges. I mean, in theory, it all sounds very nice, right? Like we have our LC task and everything gets magically forwarded. Unfortunately, in practice, we really needed to create the fuzzing task, and it's a bit more difficult once we want to have the forwarding working. Then we also, basebands are highly stateful systems, and we need to deal with complex state inside the baseband when we want to be successful at fuzzing. And also, Dyon mentioned Galaxy S10e was our target firmware, because firmware did not support anything more recent. So we have no support for recent phones in our emulation, and we need to find a way to deal with this. But let's start looking at the first challenge, creating fuzzing tasks. One core part of creating the fuzzing task is to initialize all the tasks this
fuzzing task wants to speak to. So we basically want to make sure that, in this example, LLC is ready to receive input and would be happy to process it. And this is exactly what's happening here in the code. So we allocate, using the RTOS primitives, a little bit of memory to create an init message. And we put magic values in this initialized message to then later use again the PAL message send to functionality to send it to the LLC task. The values we use here for creating the initialized message are based on reverse engineering. So it took a fair amount of time staring at the baseband to get to these values. So we did this for the LLC task, but of course the plan is to interact with all of the other ones, so we need to repeat this reverse engineering and initializing for all the other tasks. So we did it for SMS, works exactly the same, for GMM, for SS and SM, and you may already see now that I skipped one task. We could not as easily initialize the SNDCP task.
So some task, in this case the SNDCP task, actually requires some parameter negotiation, because typically you have the network and you have the phone and the network will exchange some values, and then the phone and the network will say, hey, we can actually use these values, right? But the problem is we are emulating, so we don't have this network capability. So we are actually the ones also negotiating with the emulated baseband. And in this case, we need to send a activation indication and an XID block. So it may seem a bit crazy over here. It's not even all the code. But the only thing that you really need to remember from this is that we need to set some specific values, right? So you're going to use a certain data compression algorithm, a certain header compression algorithm, certain IP type, for example. And this is then the activation indication, and then the XID block is really similar, but just with other values. But the main idea that you want to remember here is that although you need to set some magic values for these initialization messages, those messages are not enough for certain tasks. In this case, the SNDCP task. So you need to do a lot more reverse engineering to find these values and these messages.
But with all of this, what Dyon just explained, we now had the task initialized, so our plan should go up. We should be able to have fuzzing working. So let's take our fuzzer for a spin. Here symbolized by a windmill, as we are in the Netherlands. So let's spin around with those fuzzing inputs. Spoiler, it did not work yet. And we took one of the fuzzing inputs to understand what happened. We took this input and started replaying it against the firmware framework to look at the logs to understand what's going on. So we have our fuzz task sending an input to the LLC task, and we see the LLC task is just happy accepting the input, and we see at the very bottom line here that it would forward the input to the GMM task using the PAL message send to function. So that's great. LLC accepts our input. We go on. But then in GMM, things get a little bit worse. We can see that at some point it complains that the GMM state is null, and it would also even say, hey, this is an invalid GMM state. And as a result, the message is not further processed but dropped, and that's not great for fuzzing, right? We want to trigger a lot of different functionality. If our input is directly dropped, we are not getting there. So we needed to look a little bit more into what's happening here.
Now, to solve this problem, we actually need to find out what is missing, right? We sort of get a hint that there apparently is some GMM state which is null, and then the GMM task will not forward our message. So we typically use a tool like Ghidra to reverse engineer this part, because we know where this log trace is actually printed, so we can just backtrace it in Ghidra, and then we find something like the shown output here. We see a big switch statement based on the GMM state variable, which is what we call the GMM state variable. And we see that there are some values which do interesting stuff, and there is the default case if it doesn't match these interesting values. We see in the default case it will print this message. There's probably the value 0 means that it will print this debug or this log trace. So next, we now need to know how we can change this variable where the switch case depends on. So if we actually look at the variable is retrieved from a function, which is in this case what we call the GMM getState function. And the GMM getState function is actually fairly simple. because it just dereferences some memory. Okay, so now we know how we can, or where the state actually comes from, right? Because it's just a memory address at the end. But how do we now actually supply the right value to this memory address? And the other part is that this is only for the GMM state, right? But we have other tasks which also have a similar problem. In this case, we have the SNDP state, for example, which we also need to reverse engineer where this state is actually coming from. Now, the main advantage of the approach of using firmware is that the fuzzing task itself, again, is injected in the real-time operating system. And this means that we can simply do C dereferencing. We know the state that we want, right? Because we know these interesting values. So we can just dereference the memory and then supply the right values, which you can see on the right.
So having all of this done, we took the same input again and replayed it again against the firmware framework and looked at the log output. And unsurprisingly, on LLC, still everything is right. We're forwarding it to GMM. And then here, the GMM task takes the input, starts processing it, and says, hey, it's a valid message, let's forward it to the supplementary service task. So we overcome the roadblock of a missing state. The SS task then would just start processing it, and yeah, we repeated this kind of approach for all the different tasks so that we could be sure that fuzzing input can reach all of the different tasks which we have in the stack. So with all of this initialized and all of the tasks being set up, we took the fuzzer for a next spin and tried it again, and indeed it worked. So this is not a too long fuzzing campaign. We're running here for approximately 3 hours. We already found a couple of crashes. AFL++ saved 9 in the case. Some are duplicates, some not. But yeah, we had a good basis, and we wanted, of course, to know, are these crashes true positives or false positives? So we again took one input and replayed it against the emulated firmware, and we could see that after a lot of different logs messages, we will see at the bottom the message that we have a PAL memguard corruption. And this, in the context of the baseband we targeted, a Shannon-based Exynos system, would mean there has been some sort of heap-based buffer overflow, which is cool. The problem now is that this is just in the emulated firmware for a target firmware from an old phone. So we need to somehow be more confident than what we found is, on the one side, an actual true positive bug, and on the other side, that it would also work on recent phones. And we went for a somewhat naive approach here of just taking all the different crashes we found and trying to replay them over the air against newer phones in the hope that they maybe just crash. Of course, doing this manually is a little bit like cumbersome and error-prone, so we automated it by patching open source tooling. Our setup for doing this looks something like this. We have a Dell laptop there, which is used to run Yate or Yate BTS, so base station software, which on the radio front end uses the Blade RF as software-defined radio. We also have a Raspberry Pi, which connects to all the different phones we were testing, most of the time 4 phones. And we also have all of these experiments inside a Faraday cage, just to make sure that we are compliant with local regulations and don't break any laws to have rogue base stations somewhere around. As phones, in the setup, we mostly tested the Pixel 6 and the Pixel 8, as well as the Samsung Galaxy S22 and A14. Occasionally, we also switched in an S10e just to make sure that the bugs we found in the emulation works, at least on the firmware we were actually testing. But the good news is, with the Pixel 6 and Pixel 8, we could find that quite some of the bugs we found would actually replicate over the air against the newer phones. Mostly indicated by the connection bar disappearing, but also if we look at ADB logcat, we can see that there are messages of the modem crashed with 3 exclamation marks, and there's a modem state crash exit or state crash reset. So at this point, we are fairly confident that the bugs we found in emulation replicate against the newest model phones with the newest firmware at the time. And with this in mind, let's look at one of the bugs, which was just publicly announced this month. So get your October updates if you're running Google Pixel phones. Yeah.
So as a running example, we take a look at the bug that we found in the GMM task. And it's actually a really interesting one, because if you take a look at the payload itself is actually intended to be forwarded to the SM task. So it isn't even a GMM payload. But logically, this also sort of makes sense, because the GMM task will receive this message before the SM task, because the GMM task should forward this message. But apparently the GMM task does some funky stuff, and then the basement crashes. So in this example, this is a activate PDP context accept message. And we also see a very big table, and the table contains information elements. So every radio message in a baseband consists of information elements. And these elements can either be mandatory, so an M, or optional, or an O. And when they're optional, there is also a magic value for this, because the baseband will need to know whether this information element is present or not. And then finally, they can be fixed-sized or variable-sized. So we have a part of the payload in the slide as well. And if we actually match these bytes to the table, we see that the payload starts with the value A, which is, in this case, the protocol discriminator, or the first byte of our payload of the SM task. The next value is the value hex42, which is the message type for the activate PDP context accept message. Then we have the value hexFD, which is the negotiated LC SAPI. And then we actually move to a more interesting information element, because the other information elements were all of size 1. And as you can see, the size is variable. And this is the negotiated quality of service information element. So if we actually look at this information element, we see that the baseband starts with trying to access the index of the PDP address. So we see payload 3 plus 5. So payload 3 is the first byte of our quality of service information element. And this happens to be the length of that specific element. The plus 5 is actually from the 3 bytes we already parsed, right? The protocol discriminator, the message type, and the negotiated LLC SAPI. Then we have plus 1 for the length field of this quality of service information element. And then we have plus 1 for the radio priority information element. And then we have payload 3, which is the actual length of the service of the actual element, which we can see in the table now. Then the basement tries to use this, or at least the payload 3 here in this case is hexFD. But because of this additional 5, it will overflow into the value 2. So the basement next uses this, what it thinks is the PDP address index, and it will then use this value 2, which in our payload happens to be the value hexFD. So now our PDP address information element, the first byte, is hexFD. And finally, the baseband then checks whether the index is below our original size of the message, which is the value, which is n, which is 192 bytes. So the baseband passes this check, right, because it's only 2. And then it checks for this magic value, hex2b. But it doesn't pass this check, right, because the value is 2. So it will go into the next if check. Here we can see that it will pass this check, right, because the value is 2. And then our second byte of the payload, or the third byte of our payload, the second index, also happens to be greater than 2. So it will pass this if check, and then it will allocate a new message struct. It will use this value n, which is of our original message, 192 bytes. And then it will try to memset this function, or this heap block, with the value 0. The problem here is that the actual length for the memset is hexFD, which is beyond our 192 bytes of our payload. So in this case here, the overflow happens here because we try to memset beyond the bounds of our heap buffer.
So this has been quite a lot. Let's look how this looks in practice. And now I need to hope that the demo just starts playing. No, not yet. Okay. So over here we have Shiba phone, so that's a Google Pixel 8, and on the other side we have Yate or Yate BTS, our base station software. We're trying to connect to our network, and we zoom in a little bit into the network symbol to just see what happens. At this point we should be connected, right? The symbol is all black. And we see down here our patch is happening. We are sending the crashing input. And indeed, the connection disappeared. We see here the crash. While the Shiba itself thinks on the UI, we are still connected. So at this point, the baseband did actually crash. And we can also look, for instance, in Logcat to see that this crash did happen. And this is how we confirmed, like visually, that what we are doing actually does work and makes phones at the very least unavailable, if not more. And with this, let's wrap up this talk. And at the beginning, we will, for this, talk very briefly about defenses. One very good thing we are seeing these days is that vendors started to take baseband security more seriously, and a lot of vendors are pushing for more defenses being deployed. For instance, just this month, we saw a blog post of Google talking about having an integer overflow sanitizer, CFI, and auto-initialized stack variables in their newest flagship phones. Also, in one generation before, we saw in the Pixel 8 a hardened heap with an additional heap sanitizer. And even before that, like things like stack canaries, which we know from traditional computing, slowly start to arrive in baseband firmware, as well as a consistent note of the execute never, so non-executable stack bits. Another defense for especially the bug we showed here is to disallow 2G. Some phones have the possibility to do this by searching in the settings for the allow 2G button, and you can explicitly opt out to have the legacy stack being reachable over the air, which is, I think, fair to do if you are living in a region where you're not really dependent on 2G communication. Okay, let's conclude.
So to start, we believe that the parts that we analyzed in this talk have been fast and analyzed extensively before. And we believe if you find a novel way of doing baseband research, you can actually still find vulnerabilities in the protocol stacks, so even the legacy stacks. So as an example, we decided to look at Layer-2 and also added some state in there and still found vulnerabilities, even though these things have been analyzed extensively before.
And another thing we would like to point out why this type of doing more baseband research is important. Undiscovered bugs have a real long lifetime. We don't know when this bug we found were actually introduced, but the stack is more than 20 years old. So there's a good chance these kind of bugs have been around for a time. And also we found it from a firmware in 2023 and still see it's applicable in firmware from 2024. And even with cross-vendor implications, right? We targeted a Samsung firmware and could replicate the bug in a Google phone. This is because there are only a limited number of baseband vendors, and so there are only a limited number of implementations which are shared across different phone models.
Then to finally end on a positive note, we do want to stress the basebands or the shift in vendors' attention to defenses in basebands, which is a really positive shift these days. And
that has been our talk. We're happy to take any questions either here or via email or in the hallway later.
Thank you very much for your talk. We have time for a couple of questions now. I guess I have one question. Is the bug exploitable or is it just a DOS?
This one is just a DOS.
Well, this one, as we tested it, is just a DOS. As of now, however, it is a DOS because we are overflowing with null bytes. As has shown in the past, sometimes overflowing with null bytes can lead to exploitable conditions. We on our own did not found it for this particular bug, but Google regarded this still as a critical vulnerability. Maybe because under some very arcane condition, you could craft an exploit in the future with this.
All right, thank you.
Okay, thank you for a nice talk. I want to have some simple question because I'm also trying to fuzz the layer 3 and 2 of the LTE by using firmware. And when I make a task fuzzer, when I run the fuzzer, but it has a lot of false positives, and the AFL can't identify the uniqueness of the crash. So I want to ask the ratio of the first positive and the uniqueness of the fuzzer, crash. And also, have you ever tried to patch the one-day bugs or the crash app you found after that? So yeah, have you ever tried to patch the vulnerability and then rerun the fuzzer?
Okay, I think so. Let me try to recap all of the question from end to first. So first, whether we patch vulnerabilities and try to rerun the fuzzers. No, we have not done this. We usually just wait for the vendor to do the patching after we reported the vulnerability, and then we try again. Then there was a question about how many unique crashes we find versus the general distribution of crashes. It's a little bit difficult to assess. The AFL metric of uniqueness is not really unique crashes, right? So most of the times we have, I don't know, what would be, we cannot give an exact number, but I think of this 9 crashes we had in the screenshot, maybe 1 or 2 were actually unique crashes with a unique reason. And then the third question was how many false positives we encountered and what we do about false positives.
So I don't think we had a lot of false positives. The only problem or the difficulty with this approach is that you manually. I guess I can use this one. So that you manually need to add state, and you need to be careful here is that you don't overdo this part, because you may not be able to recreate that part over the air, right? You may set a certain variable to a certain value and then set another variable to another value, but these values may be contradicting and can never happen in real life, right? So with regards to that, we did not really have this issue, mainly because we did not over-engineer adding the state. It was just enough, getting just enough state to get everything running.
Yeah, and I think one additional note is that we explicitly did not start it with LTE yet, so great that you're doing it. But there you have to deal with more state, right? Like with different ciphering modes and authentication and so on. So I think that may also be a reason for more false positives or crashes, because some of the authentication state is missing.
One more question from the other side here.
Yeah.
Hey guys, great talk. When you're saying that vendors are pushing in the direction of defenses, is this because Google is pushing the Shannon baseband implementers to do this, and it's only true for Shannon, or also for the others? Let's say MediaTek and Qualcomm, or what else you find on phones?
So I have not looked lately into Qualcomm modems, but I know that, for instance, MediaTek also started in the last couple of years to take security more seriously, with having a more approachable security team you can report to and similar. So I think it's not only Google pushing for that, but I think Google plays quite a role in publicizing the different things which are missing in baseband firmware.
Hi guys, awesome work. I was looking at the firmware repository and I saw the last commit is from last year. So are these changes also coming to the public Git repository? And my second question is, did you also try to exploit one of these bugs and then pivot from the Cellular processor to the application processor?
So regarding the changes, yes, eventually we plan to make everything open source, but as long as not all of the things we found are patched, it's not great to put the fuzzers for this open source, right? So, but yeah, eventually we hope that we can publish all of this and add it as additional showcase into the repository. Regarding exploitation, so I on purpose do not do exploitation because I believe the world does not need more baseband exploits.
Okay, thank you.
All right, let's thank the speakers again.